So we will define this. Let f be a function. Generally, we take it as continuous in our applications, or continuous except on a finitely many continuous functions defined on a bounded region. Okay, let me spell it out. Bounded region, say D in R2 with boundary consisting of finitely many continuous curves. Okay, so it takes a long to write it down, but for example, D is the unit disk. Okay, so the unit disk is a bounded region. Its boundary is the circle, just one continuous curve. Or, for example, D can be a rectangle. So it should, if you are trying to generalize a theory, it should also explain the previous theory. If D is a rectangle itself, okay, its boundary consists of four continuous curves, four straight lines. Okay, so even though it takes long to write these things, it's not mysterious. Okay, so we want to understand the integral of f on D. Again, the interpretation is that if f is positive, there is a volume over this region under this graph. We want to find the volume. We want to calculate that volume using double integrals. Okay, so we define. Okay, before this, let me write the question. So we want to define double integral of f on D in a way compatible with the previous one. In a way compatible with the case when D is rectangle. Okay. So we play a small trick and we use the additional remark we put into Fubini's theorem. Fubini's theorem said that everything is nice except these things are continuous on finitely many curves. Okay. So for this, we define a new curve, a new function. Okay. Okay, let me use P, f of P. When we actually do calculations, we'll put x and y here so that iterated integrals will know which parameter to integrate. But for the idea, I'm only interested in the function. So you see that this is also the idea for higher dimensions. So this is going to be equal to our function if P is in the region and 0. I have to define a rectangle. Okay, so here I'll define a rectangle if P is in the rectangle but not in D. Okay, on a rectangle R containing D. Oh, okay, so this R is again a rectangle like this with sides parallel to x and y coordinates. Okay. You see, the idea is again very typical idea you employ in science. I understand a certain situation. Now I have a more complicated situation. I try to reduce it to the case where I know. Okay, I know how to integrate continuous functions on a rectangle. I even know how to integrate them if the continuity fails only on finitely many continuous curves. Okay, so I include D into any rectangle. I draw any large rectangle. That's where I use this the fact that I started the bounded region, so I can put this D into a rectangle. this size parallel to x and y. Now on this rectangle, I know how to integrate nice functions. Okay, so I create a nice function. You see that f is continuous inside D, or if it fails to be continuous, okay, that will be on finitely many curves. But for the time being, let's assume that f is small f is continuous. Okay, so f is continuous in D. Now this new function is constantly 0 outside the region D. Okay, so outside the region D, the function is again continuous. The only problem may appear on the boundary of D. Okay, so if the function is not 0 there, it suddenly jumps down to 0, or if it is negative, it jumps up to 0. So the boundary of D is a candidate for discontinuity. Okay, so we said that the boundary consists of finitely many continuous curves. Okay, so this function is continuous on the rectangle R with the possible exception of the boundary of D. Okay, so this function is integrable. This notation, remember that subtract D from R. Okay, so that's called set minus. That notation, if you want to find it, it's set minus. So this is outside D. So the picture is something like this. This big rectangle is R. My region is something like this. This is D. Okay. So this shaded region is R minus D. Okay. So shaded region is denoted by R minus D. You are not obviously subtracting actually something. This is set subtracting. You throw away D. What remains is that region. So I have a function defined on D here. Suppose it's positive. And suddenly on R it is 0. Okay. So we define the integral of small f on D as the integral of big F on the rectangle. You see the contribution of big F as you move away from D is 0. Big F is not contributing anything that small f didn't tell you. So we define double integral of f on D as double integral of big F on R. Okay, so this part we already covered. F is continuous on on R with the possible exception of the boundary of D. Okay, so remember this is boundary notation for boundary of D. Okay, but boundary of D, we assume that we are going to work only with nice regions where the boundary consists of only finitely many curves, finitely many continuous curves. Okay, so the theorem, the previous theorem we mentioned about the existence of integrals says that the right hand side exists. Okay, so this side, this number exists by our previous considerations. Okay, so we say that this is going to be a number and I will assign it to this number. Okay, it makes sense. The only thing to check is the fact that here this number obviously depends on R. If you look at the notation says that if you consider a different rectangle, you have to write the name of that rectangle here, but the number will not change, okay, because if you move out of D, no matter how large or how small this rectangle R is, the contribution is always 0. The function is always 0 here. Okay, so it is, we also make a note of this, since f of p is 0 if p is not in D, the choice of R containing D is not important. Is not important means that if you choose a different rectangle, if the only condition that that rectangle includes our region D, the number you obtain will not change. Okay, so that's that's again theoretically satisfying, but practically again, how do you calculate this number? Okay, so far you see that I cannot actually write this because I have to know exactly when I am outside D, when I am inside D. So the equations for this boundary must enter somewhere. Okay. So again, the question. So now, again, the big question is how to calculate this number, this integral. Okay, so now we go back to the region again. We want very nice regions. So, okay, the book uses type 1 region, type 2 region. Okay, let's also use those names, but they are not universal. Generally, after you get used to this theory, there is no need to give a name to these regions. You look at the region, you immediately know how to cut it down into nice regions. So that will also follow in a minute. So, okay, let me write it over here now. Okay, so let me change color so that you will not see it. Easily calculate these integrals. We consider only very nice regions. D. Okay, so remember that we want the boundary of D to be consist of finitely many continuous functions, so we will make it more precise. Okay, so the book calls type 1, I think the book is using this, type 1 regions. So okay, which one he calls type 1? Whether you do it with respect to x, okay, so. In the xy region. So these types are according to how you express the boundary of the region D. Okay, so from XAB, we consider this part. Now inside here, the region may have paths like this. So this is one type. So like this. Here you have a straight line, and then here you have something like this. Okay. So this side is given with y equals let me say g1x. This part y equals g2x. Okay. So this is my region D. Okay. So here g1 and g2 are continuous functions. So g1 and g2 continuous functions. Now we have the other two variations are on the length of this side. Okay, this side can be 0, while this side is not, or you can make this side 0, the length of this side, where this side is not 0. So let me draw these things without actually making any further remarks. Okay, so these 2 points can coincide, so you will have something like this. Okay, so this is one type. So again, this is y equals g1x, y equals g2x, or you can have this one. Now that I started, let me draw all of these silly things. Okay, so in one case, both of these points are like this, and here, okay, so I can have this, but I can have this here. This is D. Okay, so all of these things will be of type 1, and again the curve here is y equals a continuous function of x, and the top one is y equals another continuous function of x. These are type 1, and type 2 is just looking at the picture from this part. Okay, so type 2. So let me again draw something like this, y, and y will go from C to D, and I have this region. So the region D will lie inside here. So again, let me do this one. So it will be something like this. Okay, so this is my region D. So this part is, I'm looking to life as if I'm living on the y-axis. So what I see two curves. Okay, given y, I know immediately where I will land on this thing. So the equation of this curve is a function of y. What does the function of y give me? It gives me the x coordinates. So x equals h1 of y, this curve. And this curve here is x equals h2 of y. Okay, so h1 and h2 continuous functions. So again, the length of these sides can be, these are straight lines, so they have lengths. The lengths of these sides can be 0. Okay, you see all the variations here. I played with the length of this side. Here both lengths are, none are positive. Here this is 0, here this is 0, here both of them are 0. Okay, so again, let me make a note of this instead of drawing all these things. Okay, so this side and this side, the length of these sides can be greater than or equal to 0. Okay, so when they are 0 or not, no double integral alırken sorun çıktı. Bak. Bak canım şey kaldır. Okay, so these are the nice regions. In most cases in calculus, the regions will be so cooked up that when you change your point of view, the region will be both region of type 1 and type 2. For example, if you take a circle, it is both type 1 and type 2. Only the expressions of these functions change. And in fact, if it is a circle, the function is exactly the same, except that you change the places of x and y. Okay? And in particular, those types of regions where it can be seen both as a type 1 region and type 2 region will be interested for the sake of exercises and problems in calculus, because the main question, the main technique that you should get from here is interchange the order of integration. Okay, because once you set up an integral correctly, nowadays you are not responsible to evaluate it by hand. You can use a software, a reliable software, because some softwares are known not to solve certain types of problems correctly, but they solve other problems correctly. So your responsibility is to recognize these softwares, set up the integral correctly, and then give it to a software. And if the software finds it difficult to evaluate, then you have to reverse the order of integration and try again. Okay, so the chances are that one of them will be easy to solve for the software. Okay, so my generation and the generation coming after me, we couldn't succeed in writing software where you read the problem to the software and the software sets up the integral. Okay, so it is your responsibility to write up software like that, and then the problem of calculus students will be different. You tell them what to do. Now, I tell you that your responsibility is to set up the integrals correctly, and if necessary, to reverse the order of integration correctly. Reversing the order of integration in a rectangle is trivial. You just change the places. But here you see it will not be easy. Okay, so for example, if if I try to see this as a type 2 region, from here you see I have several choices. I have to cut it down. So, okay, let's also write that. That's written at the very end of the section here, but I'll write it here so that we can attack these problems now with more confidence. Okay. So our region of interest may not always be a type 1 or type 2 region, but it may be possible. So in most problems we are interested in, it will be possible to write it as a union of type 1 and type 2 regions which touch each other only at the sides, only at their boundaries, at their, let me say, at their boundary points, because sometimes they touch each other only at a corner, so that's just one point, at their boundary points. Okay, so boundary points will consist of nice curves, and along a curve an area is 0, so it will not contribute anything to the integral. Okay? So for example, a typical example. Okay, so I'm drawing this. So let's try to do something like this. Okay, so suppose we have something like this. Okay, I don't want to exaggerate this, but this part. Okay, so x, y. Okay, so I see here that if I take this, then I have this curve up to here. So this is strange, so let's make it like this. So from here, well, I can go up to here. Okay, so this is, say, C, D, 1, and then here I have this. Okay, so for, okay, let's also make this, now that I started this example. Okay. Okay, so, and then this one, D1, D2, D3. Okay, so this region you see is of type 1. So let's say this one is type 1. Okay, I have a curve here and I have another curve here. But this is type 2. Okay, so let's say type 2 green. So this part is type 2, because when I look at this way, I see this curve and this curve. And this one, I can do it both as type 1 and type 2, okay? Because I can look at it like this. So I have this curve and I have this curve. It is type 1, okay? Or I can look at it from here. I have this curve from here and this curve from here. So this turned out to be a nicer region than I thought. So let's say, okay, let's use another color here. So purple, both can be considered, can be seen both as type 1 and type 2. Okay, so now you integrate the function here, here, and here, and add them up. So let us give them names. Suppose this is region D1, D2, D3. Our region D is union of D1, D2, D3. Okay. The regions D1, D2, D3 intersect each other only at their boundary points. the technical terminology for this is that the intersection has measure 0, so it will not contribute to the overall integral. When you are doing double integrals, your measure is area. These things intersect along curves. The area of a curve is 0. Okay, so it will in the Riemann sum. If you consider the Riemann sum, okay, so when you are taking smaller and smaller rectangles to cover this line, eventually the rectangles will go. The area of the rectangles will go to 0. So in the Riemann sum, they will not contribute anything. Okay. And this is the important part. Double integral of f on d is equal to double integral of f on d1 plus okay, so this is one of the properties of double integrals. Yes, question? So this one I wrote type 1, this one I wrote as type 2, because I look at it, I can also write it as type 1. Yeah, okay, so let's also put the arrow here. Okay, so this can also be seen as type 2, type 1. Okay, so it is very important to recognize that you can see it as both type 1 and type 2, because I'm repeating, this is the main technical responsibility that you should have to change the order of integration. Okay, whether you see it as type 1 or type 2 is important in the integration, and sometimes if you see it as type 1 and set up the integral, it is very difficult to evaluate, or sometimes even impossible to evaluate in terms of simple elementary functions. So you have to switch your point of view and set up the other integral. Okay, so this is one property of the integrals. Before we have other properties, but first let us concentrate on this. First let us write integrals. How do I write the integral on a region like this? Okay, so so the question is now, I have a type 1 region. How do I write the double integral for them? Okay, so question. D is a type 1 region. F is continuous on D. How to evaluate double integral of f on d? So that's the question. The main tool in these things is Fubini's theorem. Fubini's theorem says you have to use, well, not you have to, you can use iterated integrals. Okay. Fubini's theorem in the case of a rectangle is very easy. So what we are writing here is a version of Fubini's theorem in the case of a type 1 region. Okay. So Fubini theorem for type 1 regions. So it is always important to draw a picture, because even when you become professionals, it's misleading to try to imagine these things in your mind. So this is a type 1 region, so x changes from A to B. Okay, so the region, let us say the region is something like this. Okay, so it goes like this. So this is y equals g1x. And let us do this. This is y equals g2x. This is the region. Okay, so first of all, let us forget about f. Suppose f is constantly 1. Okay, so what happens if f is constantly 1? I integrate f over this. So whatever the shape of the region D is, I am considering a cylindrical box with height 1. Height is constantly 1. Okay, so I'm multiplying the if you look at the Riemann sums always uses areas of rectangles which fill out this region. Okay, so in the limit, those rectangles calculate me the area of the base. I'm multiplying the area of the base with height. Height is 1. So the number I find is the area of the base. If you put units, okay, it's say cubic centimeters. If it is 5 cubic centimeters, that's the volume of this thing, but 5 is the area of the base. Okay. So first of all, let's assume that f is 1. I want to calculate the area of this using last semester's techniques. First, I take an arrow, a typical arrow like this. Okay. Consider this arrow. Okay. Consider a typical arrow parallel to y-axis. Okay, so I keep y in mind. This enters the region here. Okay, so this arrow enters the region when y is equal to whatever this point is. Okay, so I'm drawing this typical arrow at a point x in between A and B, okay, at a typical, at a, let's say general point x in A, B. Okay. It enters the region corresponding to x when y is equal to g2 of x, when y equals g2 of x, and leaves the region when y is equal to g1 of x. Okay, so if you subtract them, you get the length of this thing, this line segment. If you multiply it with the dx, okay, you get the thickness. You add them up, you get the area. Okay, so we'll do the same thing here. Then first I look at, okay, so double integral of f on this is equal to, first I have dxy dy. Okay, that's why I put this into a box. If I draw my arrow parallel to y-axis, I am first integrating with respect to y, okay, because the expression is given in y. This enters the region when y is equal to g2 of x, and leaves the region when y is g1 of x. Okay, so then we'll integrate with respect to x, but let's pause here. After we evaluate this integral, if we are lucky, if it's a cooked up example, we immediately find an antiderivative for f. We put the endpoints, simplify, we obtain a function of x. Okay, so this must be one of your checkpoints. At this point, you must obtain a function of x. If you are integrating with respect to y, when it is finished, in the expression, y should not be c. Okay. Now, next, we integrate this with respect to dx. Okay, so this function. So let me use this purple again. Today it looks very nice. Okay, so this is a function of x alone. And repeating the same thing, no y appears anymore. Okay, if a y appears here, you made a simple mistake somewhere. Check it and correct it. Okay, now I have a function of x. I integrate that function of x with respect to x. And what is the range of x? X changes from A to B. Normally you find this, of course, when the region is given, it will not be given as cooked up like this. A and B will not be there. You'll decide what A and B is by asking the simple question. For which values of x does this statement hold? Okay, if I choose x here, obviously a typical arrow does not even touch the region. Okay, so all those things are out. Starting from x equals a up to x equals b, a typical arrow cuts the region, and in fact the boundaries are well defined. So the range of x is from a to b. Okay, so that's what we write. Okay, so this is integral x equals a to x equals b. Okay, so again, when it is all over, let me again use this color. Okay, this is a number. Is a number. Okay, so if this turns out to be a function of y, or if there are a few x's and y's floating around, again, you made a simple trivial mistake somewhere. Okay, so go back and just correct that mistake. Of course, in more complicated problems, the function f can be a function of x and y, and there may be a parameter t. But if there's a parameter t, then this is going to be a function of t only, not a number. But again, this if I put like this number here, remember you are integrating with respect to x and respect to y. When you are integrating with respect to y, anything that's not y is a constant. So in particular, t is a constant. Then when you come here, you only have your parameters and x. Anything that's not x is a constant. You integrate with respect to x, x disappears, and all x's are replaced by numbers. Now, if there were parameters which you treated as constants, that they will show up here. Okay, but we will deal only with very few problems like this. But in your real life, such things will turn out. So don't sue me because I say the number here. You see, I put it between brackets, between quotations. So it's a number with respect to x and y, with respect your integration parameters. Okay, so these are totally trivial observations, but sometimes when you are in a hurry, you make a mistake, an answer comes out, and in the answer there are some x's and y's floating around. Okay, so that's one checkpoint. You just go back and correct the error you make. The error you make will be the following. Now, reverse the order of integration in a hurry. And most definitely in the exam, you'll take this, put it here, and takes this, put it there, and just change their positions, and then you'll integrate. When you integrate it, the answer will be a function of x. Okay? So let me make a note of this. Suppose now in the second example, our region is both of type 1 and type 2, so we can set up the integral in both ways. Let's do that. Again, I will not use any explicit formula. I'll do it like this. Okay, so, well, this is Fubini's theorem for type 1. Type 2 will be the same thing. Okay, so you'll draw with arrows like this. So next, assume D is both of type 1 and type 2. Okay, so let's invent a nice region like this. Most of the time these regions look like an ellipse. Okay, so our region will be something like this. Okay, so I'm drawing it as a circle, but okay, so when you look at it as type 1 from A to B, so this part is y equals, okay, let me use this one, g2x. This part is y equals g1x. Okay, but when you look at it as type 2, so it will be from here, from C to D, and this part now, this thing is x equals h1y, and this part here is going to be y x equals h2y. Okay, given y, I know what the x coordinate is. Okay, so this is my region D. So the double integral, so again, this is Fubini's theorem. This is the full version when it is both type 1 and type 2. F doesn't go there. Everybody should know its place. Okay, so this is D, this is F. Okay, so the first one, by looking at as a type 1 thing, I take a typical arrow. Okay, so let me take my typical arrow. So I take my typical arrow at the point x here. Okay. I'm integrating this. Okay. I'm integrating f of x, y with respect to y because my arrow is parallel to y-axis with respect to y. And y equals g2 of x. It goes up to g1 of x. Then I integrate it with respect to x. And this makes sense when x is between a and b. Okay. Then I take again fxy. This time I want to integrate it with respect to x. So I take an arrow. This time let's take a green arrow. Huh? Question? Okay, I take an arrow parallel to x-axis at a typical point y. Okay, this is parallel to x-axis, so I'm integrating with respect to x first. It enters the region when x is equal to h2y. h2y. It leaves the region when x is equal to h1y from here. Okay, so it enters the region here, leaves the region here, and I read the formulas. Okay. And this makes sense, this description of the region makes sense when y is between c and d. Okay? So between c and d, integrate respect to y. Okay, now observe that in both cases I'll get a number. All x and y's are eliminated in integration. I get a number. The claim is I get the same number, which is again something that we can prove. If f is positive, we are talking about a volume, so we can calculate the volume by slices in either direction and get the same number. So that's the proof of this when f is positive and continuous. Okay, so what you should see here is that going from here to here is called reversing the order of integration. When you reverse the order of integration, you see that this g1, gx does not come here. Okay, so this, let me do this in red, because this is something which you will do in the exams, and then after the exam you will laugh. Okay, after the exam when we read your papers, we also laugh. If there's no fun, nobody will read exam questions. I should tell you what you wrote for question 1, you will be surprised. Okay, so what was the first question in the midterm exam? Calculate the limit of simple. Yes, there are people who took second derivatives, compared the second derivative, mixed derivatives, and then filled the page with calculations. And then, as a result, of course, before you pass to the next page, you must say something. Then from there you conclude, not you, but this is one page, the limit exists, or the limit does not exist, and then passes to the next chapter. Okay, so that's, instead of doing that, you just turn to the next page. Why are you wasting your own time? You look at the problem, you realize that you are not, that's not something you studied, so don't waste your time, pass to the next page, okay? You don't have to do something. But this is again one of those things we will do in the exam. We will give you this description and we'll say evaluate it. The function will be such that an antiderivative with respect to y is impossible to obtain, but you immediately recognize that an antiderivative for x is easy. So you have to calculate this integral. But in the stress of the exam, you do things that you normally don't do. So this is one thing that you normally don't do. You just reverse the order. g2x, g1x, a, b, f of x, y, dx, dy. Okay, so when you evaluate this, since this is a cooked up exam question, you'll immediately find an antiderivative of this with respect to x. Put x equals a and b, evaluate them, but now what you have is y. Okay, so again, you are, everything is going correctly. Now you have a function of y. Either you will have problems in finding an antiderivative of this, or if you are lucky, these constants somehow killed the difficult part. You find an antiderivative of the resulting function of y, and you evaluate it from here to here, and then what ends up is a function of x. Okay, because at the very end, instead of y, you put x's, you obtain a function of x. But what was the general rule? You have to obtain a number. Okay, so normally at this point you wake up and you say, look, wait a minute, what am I doing? This is not the case. I have to draw the picture. Okay, so we have 1 minute, so I'll just mention this and we'll stop. And on Thursday, I'll solve problems about all these stories. Okay, so how to reverse the order of integration given this integral? From this integral, you draw this figure. Okay, the idea is very simple. The curves are given. This is, you are integrating with respect to y, so you draw the curve y equals g2 of x, and then you draw the curve y equals g1 of x. Okay, they enclose the region, and then you check the values of x. Maybe not every part of that region is involved. Only some part is asked. Okay, so you'll know the region by reading this, and then you reverse the order again. Starting from here. Given this integral, you draw this, and looking at this, now instead of this arrow, you draw the other arrow and write this. Okay? So reversing the order of integration definitely involves first passing to a picture, which we will do on Thursday. Okay?